All right, here's our second help video over 5-8 questions on electron affinity, and this is practice set number 2, part of the 5-8 assignment. We're picking up with question number 7. In question 7, they're giving us the electron affinities of boron at -27 and aluminum is -43. If you remember, boron and aluminum are actually in group 13. If we look over here, this is group 13. You see the 13, and it's also labeled Roman 3. Roman 3, and that A means that it's part of the main block. If you notice here, they have 1A, 2A, 3A, 4A, and then the ones in the middle, they gave B's to. The B's mean that it's not part of the main block. They give an A to the main block. But 3A, that Roman 3 is telling us that they have 3 valence electrons. They would have 2 in their S, and they're the first column of the P, so they'd have 1 in the P. So boron would be 1s2, 2s2, 2p1. Aluminum would be 1s2, 2s2, 2p6, 3s2, 3p1. So they're both having 1 in the P. Now, why do we care about that? Because we need to come up here and take a look at why they gave us a -27. Why is this one -27 for an electron affinity, and this is -43? -43 is saying that aluminum, when given an electron, will release -43 it will release 43 kilojoules of per mole of. Boron will release 27 kilojoules of energy per mole when boron's given an electron. So in other words, aluminum is releasing more energy per mole when given an electron than boron. Now that's kind of interesting for us, because the trend for electron affinity is that it will decrease top to bottom through a column, which we call a group or family. So overall, the trend should be lowering. So as you go all the way from boron down to the bottom of the table, I don't know if we have a bigger, here we go. Here's boron. As we go from boron to aluminum to gallium to indium to thallium, aluminum, gallium, indium, and thallium, that electron affinity is decreasing. But from boron to aluminum, it's increasing. So the pattern overall, chlorine, bromine, iodine, astatine, the electron affinities are going down. But from fluorine to chlorine, it's going up. So it appears from the second period to the third period, the electron affinities could be going up. Here's oxygen, sulfur, selenium, tellurium. Sulfur, selenium, tellurium, it's starting to go down. But oxygen to sulfur, it's going up. So for some reason, the electron affinity is going up from the second period to the third period, but it's dropping from the third period down. Why is it dropping from the third period down? Well, we know the atoms are getting bigger. The bigger the atom it is, the less able that atom is to attract an electron to it. So electron affinity is measuring how much energy it takes for the atom to attract and hold the electron. The better it is at attracting and holding it, the greater is the electron affinity. So boron is smaller than aluminum. So why is it that boron has trouble attracting and holding it? It has more trouble than aluminum does. And let's see what the question reads. Question 7, the chart shows boron has a lower affinity than aluminum. Why? What answer best explains it? Letter A, aluminum has a smaller radius than boron, enabling it to attract the electron. No, the size actually gets bigger. Aluminum is bigger than boron. As you go top to bottom, the atoms get bigger. So the fact is, aluminum's actually bigger. So that doesn't explain it. You don't need to know these numbers, but aluminum is 143 picometers, boron's 85 picometers. Boron's smaller. It should be better at attracting and holding it. It should give more energy off as it gets the electron, but it doesn't. Letter A doesn't explain it. Letter B, aluminum is able to satisfy the octet rule, whereas boron is not. Wait a minute. They're both, as we just mentioned, s2p1s. They both have 3 valence electrons. Getting an electron would give them 4. They would need 8. It's not going to satisfy the octet rule for either of them. In fact, aluminum is better at losing 3. If aluminum has 13 protons, it starts with 13 electrons. If aluminum loses 3 of those electrons, it would be left with a stable configuration like neon. So aluminum would need to gain 5. Boron would need to gain 5 to satisfy the octet rule. They're in the same column. They need the same number of electrons to achieve stability. Letter B is not right. Let's look at letter C. We know boron is smaller. It's 85 picometers. Could it be that boron is so small that its electron cloud is more compact? So compact means that it's so small that its electrons are not taking up much space. So to give boron another electron would require that that electron squeezed into boron's electron cloud. As we try to add an electron to an atom, the electrons that are already there will try to repel it. So boron might be so small that its electrons are more compact, giving it a greater opportunity to repel it. And that is the reason why. So when we look down on this graph here, which is a very nice graph, when we looked at this graph right here, why is it that the second period has, although they're smaller, we would think their affinities would be bigger? The smaller you are, the easier you can attract and hold the electron, which would allow you to release more energy. Well, that's not the case. The second period is too small, so that when we try to give carbon an electron, carbon's electron cloud is so compact that it takes a little more energy to force it in. Silicone is bigger, it takes less energy to force it in there, so it can release more energy. The third period has greater affinities overall than the second period because the second period is too compact. But the rest of the trend, top to bottom, is the affinities go down. After the second period, the affinities go down because the atoms are getting bigger, which means that they're not as good as attracting and holding it. Their affinities would be smaller. Let's look at the other answers to C. What about D? Electron affinities tend to increase top to bottom. No, overall they tend to decrease top to bottom because as they get bigger, they're not as good at attracting and holding the electron. Letter E, aluminum has a stronger nuclear charge. That's true. Aluminum's nuclear charge would be 13. Boron's is only 5. Aluminum has 13 protons. Boron has 5. So those 13 protons gives aluminum a stronger nuclear charge. What does that mean? The stronger the nuclear charge, it might be able to attract the electrons better. So let's see. Aluminum has a stronger nuclear charge. True. It would make it better at repelling. No. The stronger nuclear charge would make it better at attracting. The stronger nuclear charge would lower the electron affinity. No, the stronger nuclear charge increases the affinity. The better you are at pulling the electron to you and holding it, the greater is the affinity. And that's the reason why when we move left to right across a period, the affinities tend to increase. Why? Because there's a stronger nuclear charge to attract and hold the electrons. That takes care of question number 7. Oh no, number 7 we have AB. Answer AB. Boron has a high shielding effect. What is shielding effect again? Shielding effect is when the inner levels shield the outermost electron from being held. The shielding effect would also shield the nucleus from attracting an electron to it. So when you have very large atoms, we have lots of electrons in the way. Would boron have a big shielding effect, a great shielding effect, or high shielding effect? No, boron has a really small shielding effect. Why? Boron only has 2 levels. If it only has 2 levels of electrons, it only has the first level, the 1s, to shield. The 1s only has 2 electrons. Boron has a ridiculously small shielding effect, not a high shielding effect. Shielding effect does lower electron affinity. But boron has such a low shielding effect it's not even going to come into play in terms of whether boron, it's not going to ruin that affinity at all. Larger atoms have a greater shielding effect. All right, now we are ready to move on to question number 8. Which of these 4 factors influence affinity? Well, we already talked about nuclear charge. Nuclear charge does affect electron affinity. The stronger the nuclear charge, the more protons you have to attract and hold electrons, which would be higher affinity. Radius. We already talked about the size of an atom. Bigger atoms have trouble pulling electrons to them, so they have low affinities. Small atoms are great at pulling electrons to them, unless they're too small, like the second period. But smaller atoms attract electrons to them, giving them greater affinity. Configurations matter. Does the atom need the electron, or does the atom not need the electron? If the atom needs the electron, it will have a high affinity. How would it need it? It would give it a stable configuration. It might complete the octet rule, or it might fill the P, the D, the F sublevels, or the S sublevel. So when we look at this chart right here, the halogens need an electron very bad, so they have extremely high affinities. If the halogens get an electron, they're stable. The noble gases are already stable. They do not want an electron. They would have positive affinities. So the electron configurations matter greatly. The S1 column would rather lose an electron to be stable, but if we give the S1 column an electron, it would fill the S. A filled S is better than not a filled S. Right here, carbon's family, they're S2P2. If we give them an electron, we would make them S2P3. We learned that a half-filled P is better than a not half-filled P. A half-filled D or a half-filled F is better than a not half-filled. So does the electron configuration matter? Absolutely. Shielding effect influences electron affinity. Once again, large atoms have a greater shielding effect. The interlevel electrons get in the way or block the pull of the nucleus. They shield the pull of the nucleus on an outer electron. So atoms that have large shielding effects have difficulty attracting electrons and holding them, which give them low affinities. Smaller atoms do not have lots of electrons in the way, so they'd have greater affinities. All of these are true. Answer E, all of the above are true. That's the statement that best describes factors that influence electron affinities, and we will stop on question 8 with this page.